everyone. It's my great pleasure to welcome Professor T.S. Mahesh of IISER Pune to our midst. So he will be giving a colloquium talk titled Long Live the Qubit. Mahesh completed his bachelor's degree from JCBM College, Sringeri, Karnataka, and his master's degree from Mangalore University. And after completing his PhD from the Department of Physics, IIC Bangalore, he did postdoctoral research at MIT in the US and subsequently at the University of Dortmund in Germany. Since year 2007, he has been a faculty member of physics at IISER Pune. His research group at IISER explores the quantum world via magnetic resonance. Using magnetic resonance, they study quantum information, quantum control, quantum computing, quantum simulations, quantum many-body effects, and quantum foundation. Mahesh.
Thank you. Thank you very much, Professor Reggie. Good afternoon, everyone. And so I hope this will be an interactive session. Please stop me if you have any questions or doubts or need any clarifications, or if I make mistakes, please stop me. Okay, so since this is colloquium, I modified the talk a little bit from the seminar topic to a little bit widened for wider audience. So yeah, let's see if you have any questions. Especially this talk is designed for students, so experts may get bored, but so students are welcome to stop me anytime. Okay. Okay. So the topic is about long-lived states. So, and I am going to talk qubits and spins synonymously in this talk, and you will see why. And so we call this as long live the qubit. Okay, so now let me briefly introduce qubits, and most of you know, but for sake of completeness, so let's start with the qubits. So before that, let's start with bit. Bit, as you know, okay. I should not press full. I should press. Okay, lightly. Okay. I see. Oh, it went somewhere else. Where did it go?
Just a second. You can use this one. You can take this. 1 second. You can use this. This has it. You can use backward forward.
Yeah, that's better. Yeah, this is better.
That front will be less.
Yeah. Okay, so bit is a unit of information. It's realized by two-state device such as a transistor, and that is what makes up all these computers. So these are digital devices which are all made up of bits. Okay, so these are binary systems. So they are all based on two states which are labeled as 1 and 0. It can be cut off and saturation states of a transistor. Okay, so they are electronic devices. So a transistor is always in either 0, that is cut off, or in saturation, that is 1. Okay, never in between. If it is in between, then it's a faulty transistor. So that's the way it is set. So either it is 0 or it is 1, and that's how it encodes information. So it encodes information in all the information in terms of ones and zeros. Now that's the classical information we say, because there is no quantumness involved in this. At the level of information storage and manipulation, there is no quantumness involved. So it's either in this or in that state. So that is the classical information. Now, so there is a revolution in this in last couple of decades. So that is to move from classical information to quantum information. So if we now consider a quantum system, a quantum two-level system, so then, so we have two states, say, so this is up state and down state. So these are two states of a quantum system, whatever the system it may be. But because of the quantumness, the system can exist in some kind of superposition, in a coherent superposition of these two states, right? So that is the capability of the quantum system. It can simultaneously exist in wavy superposition of these two states, and that is something that is beyond the capability of a normal transistor. And then the question was asked whether this can improve the information manipulation, and it turned out that it can bring a lot of capacity beyond the capacity of the quantum information processor, classical information processor. So that is the basis of quantum information, because now we have quantum states involved. So we can do certain tasks much more efficiently, certain tasks which are beyond the capability of normal classical computers, or beyond the complexity that is handled by normal classical processors. So that can be achieved in such kind of states. So that is a qubit now. Qubit is a two-level quantum system. Now, mathematically, we can represent the two classical states that we talked about, either 0 or 1, as 2 points on a sphere, 2 poles, whereas qubit mathematically can be represented on any point on an unit sphere. Okay, so how many points are there? There are infinite points. And so qubit can take infinitely many possible states, and they are all legal states, they are all allowed. And that's one of the things why quantum information can become more exciting, because it is not just two states, all possible states are there. Now you have to cleverly manipulate it, because when you measure, it will either collapse to 0 or 1. Okay, so at the end of the computation, it is always either 0 or 1, but in between you have access to entire space. So you can move around cleverly throughout the space, throughout the Hilbert space. Now at the end of the measurement, the algorithm is designed such that it will collapse with high probability to the expected answer state. Okay, so that's the whole idea of qubit. Okay, so now qubit is the basis for many of the upcoming quantum technologies, future quantum technologies, including quantum computing, quantum simulators, quantum sensing, and quantum communication, teleportation, and there are a host of technologies which are promising potential technologies which are coming up. Okay, so I'll not be talking about all of these. So I'll be talking about some specific things in this talk. So before that, there are many, many qubit candidates. Okay, so for example, there are superconducting loops, trapped ions, silicon quantum dots, topological qubits, diamond vacancies, photonic qubits, and so many qubits are there. And every qubit architecture has some of the advantages in terms of memory, in terms of controllability, in terms of readout efficiency, and so on. So every architecture has its own pros and cons. That brings me to NMR qubit. So this is the nuclear magnetic resonance qubit. So this talk is entirely about nuclear magnetic resonance qubit. Okay, so what is it? It's an ensemble of some sample which may be in liquid, solid, or some kind of oriented systems like liquid crystals, of about 10 power 15 nuclear spins. You are not handling one spin, you are handling 10 power 15 atoms or molecules. And so that is placed in a very strong magnetic field. Okay, so that is the system. I'll give more examples. So for example, this is chloroform. Okay, so CHCl3, so there is carbon here, hydrogen, and 3 chlorines. And so there is no electronic magnetic moment. It is diamagnetic. All the compounds that we take are diamagnetic. So there is no net electronic magnetic moment. Now what leaves us is the nuclear magnetic moment, because electronic magnetic moments, they all cancel out each other. Okay, so total angular momentum, spin angular momentum is 0. So what leaves us is with nuclear magnetic moment. Okay, so now if we take hydrogen here, hydrogen has proton, and proton has spin half. So it has a spin angular momentum. Okay, and since it is spin half, it has two eigenvalues, plus half and minus half, and so it is a two-level quantum system. Okay. So now we place it in a strong magnetic field. We take about 0.5 ml of sample. So we place it in a very strong magnetic field of the order of few Tesla. Okay, it can be 10 Tesla, 20 Tesla, and so on. So we place it in such a strong magnetic field, 10 to 20 Tesla, and then so there is a Zeeman splitting of the two levels. So you have plus half and minus half. Say plus half is the ground state, minus half is the excited state. So and these levels become non-degenerate in the presence of a strong magnetic field, that is the Zeeman effect. And this is the Zeeman energy gap, and that happens to be, for this strength of the magnetic field, that happens to be in the range of radio waves. Okay, so that is about 0.5 gigahertz to 1 gigahertz. So now we have the two-level system. We can cause transitions, we can induce transitions, we can control the state by using radio waves. Okay. So now we can call the ground state as 0, and we can call the excited state as 1, and now that's our qubit. Okay. So now we can explore the complete unit sphere I talked about, all the points of the unit sphere, that is called the block sphere, just by applying suitable radio wave pulse. So we can take the state from any point on the block sphere to any other point. Okay. So we can explore the complete Hilbert space using these radio waves. Okay. We can take the qubit to any desired state. It can be done very precisely, yes.
So you have,
Yeah.
so you said that you have 10 to the 15 years.
Yeah.
So are we assuming that they're all aligned? They're either all pointing up or
No, they are not. So the sample, that's a good question. Actually, the sample is at room temperature. So there is some population here, some population there. Okay, there is a Maxwell-Boltzmann distribution. And so now what matters is the population difference, because that is what gives the net magnetization. Okay, so there is a, so all spins here are oriented parallel to the field, all spins here are oriented anti-parallel. So there is a net magnetic moment along the direction of the field. Okay, so that is the magnetization, and that is what we control. Okay, so that is the state. So there is an average magnetization, and that is what we are going to use. Yeah. So now let me take you through some stories. Okay, so I think it is, yeah. Two-level approximation is perfect. So this is different from superconducting qubits, for example. Actually, they have unharmonic oscillator with many, many levels, and they make the approximation of lowest two levels as qubit. So there is an approximation involved, because if you actually see what happens, there will be some transition leakage to third level, fourth level, and so on. Those are all ignored. But here it's perfect, okay, because it is a spin-half system, and there is no third level.
The nuclear spin, it also has interaction with the spins of your electrons, right?
No, and that's what. Electronic magnetic moment is 0 in this, because it is a diamagnetic sample. There is no net electronic magnetic moment.
But there are many electrons.
So they cause something called...
fine structure is not important.
No, fine structure is also not there. That's what. To have the fine structure, you need to have electronic magnetic moment. Okay. So there is no electronic magnetic moment. If you take diamagnetic substance, there is no net electronic magnetic moment. So we don't take paramagnetic substance. Okay. We take only diamagnetic substance. Of course, there are some effects due to electrons. I'll talk about that. So they cause a second order effect. So like they cause the noise. Okay, we'll come to that noise. Yeah, yeah, we'll discuss about noise. Yes, exactly. So they cause relaxation. Yeah. Sorry. Okay. So I'll be talking about some stories. So I hope you'll find it interesting. So this is about 15 years after Stern-Gerlach experiment. Stern-Gerlach experiment came in about 1921-22, and in about 1936-38, so Isidore Robbie, what he did was, at that time there was a idea, maybe nucleus also has a magnetic moment, because it was established that electrons have the spin angular momentum, but it was not clear whether nuclei also have spin angular momentum or not. So that was the stage, and there were some theories, and so those theories need to be checked. So then Isidore Roby, what he did was, he did a very clever experiment, a very ingenious experiment. What he did was, he took a pair of Stern-Gerlach setup, okay, back to back. So it is, instead of one Stern-Gerlach experiment, you take two Stern-Gerlach experiments. So two setup. So this is an inhomogeneous field. This is another inhomogeneous field. But in between, you have a homogeneous field, magnetic field. So in Stern-Gerlach experiment, what you see is, if you send a beam of atoms, okay, so it is basically electronic magnetic moment that was discussed in the Stern-Gerlach experiment. So it splits into two, right? Because depending on the spin, right? So because of the inhomogeneous field, the spin half goes in one direction, spin m equal to half and m equal to minus half goes in another direction. So the beam splits. So, but then he took diamagnetic gas, okay, diamagnetic beam of atoms. So now there is no electronic magnetic moment. So if this splits, it must be due to nucleus. Okay, so that's the idea. So what he did was, so he let it split, but then he took opposite inhomogeneous field in the second setup. So this was in one direction, that was in the other direction. So then they must come back. Okay, so initially the beam splits and it should come back, right? And if that happens, then we should get 100% detection, right? So that is 100% detection. But then if it is a nuclear spin, and he was interested in what is the finding the resonance, okay, finding the energy gap. Then in this inhomogeneous part in between these two fields, if you put a radio wave coil, they had roughly estimated what should be the range, and they put this coil and they tried to cause resonance here, and they tried to flip the spin. Okay, half becomes minus half becomes plus half. In that case, this converging back, that will fail, right? Because you have positive gradient and negative gradient. So you were getting 100% signal, but now you have flipped the spin. Okay. So at the point where you have flipped the spin, now it no longer converges. So that's where the detection should drop, right? Because you have flipped the spin, now convergence won't happen. So that's how Rabi found the nuclear spin. He established the nuclear spin gap in the presence of this homogeneous field. So that was the first direct evidence of the nuclear magnetic resonance. So here is the nuclear spin in homogeneous magnetic field, and you have flipped it, caused resonance, and you have flipped plus to minus. And so that's how you observe the resonance. So that's the resonance. Okay. Now that was in 1944. By the way, he got Nobel Prize in 1944. Okay, that is soon after. And then in 1950, in about 1946, that's about 4 years later, people wanted to see whether bulk systems also have this. Okay, so can we observe magnetic resonance in bulk systems? Because of course you have molecular beam, atomic beam, you can see the resonance, but what about bulk systems? Okay. So Bloch and Purcell, they are from different coasts of US, West Coast and East Coast, and they set out to do this experiment, and they independently observed nuclear magnetic resonance in 1946. In fact, this is the time of World War. World War had just ended, and so they brought radar apparently from submarines. Okay, so old submarines, lots of submarines already. So they brought this, already radar was developed already. And so they brought all these unused amplifiers, radio frequency amplifiers. That was the time that radar technology really helped these RF amplifiers. Before that, such strong RF amplifiers were not available. So they both brought and started working on this. So they both worked on the Manhattan project. And interestingly, Purcell in Harvard, so he says that in his memoir, on the evening of Thursday, December 13, 1945, using paraffin, So that's the sample. Until about 4 a.m. on Friday, so that's moral number 1. So most of the experiments work in the night. So they swept the magnetic current without any signal detected on December 15, still without any sign. So it's 2 days now. So from December 13 to December 15, still without any sign. Before shutting down, they turned the generator of the oscillating magnetic field up to its top output of 100 amperes and brought the current down slowly, and at 83 amperes they saw the resonance. So this is a moral for students. So how hard some experiments can be, but that is a revolutionary experiment. So that is the first time people found magnetic resonance in bulk systems. And then around the same time, so this is December and this is January. At that time, publication was not that easy. So you had to send it by mail, and it goes to referees again by postal mail. And then it's a long process. Publishing was, I think, several months process. So this is before, not the days of electronic communication. So they probably wouldn't have heard about these two experiments in December. So Bloch continued his experiment and in early January, Bloch prepared the magnet. In the cyclotron laboratory, they worried about spin lattice relaxation. I'll come to this later. So that's the noise you were talking about. Leaving their water sample in a magnetic field for about 24 hours before the experiment, when the sample was placed in the probe and subject to the oscillating magnetic field, nothing was detected. After about 2 hours, experimenters decided to turn up the current to the magnet much higher than the region. So again, the same story. In which they had expected to see the resonance, and let the current slowly drop. Only at that point did the researchers saw the resonance. So again, very interesting story. So they both share the results later, and they found initially actually they wrote different papers in different language, saying it's a different phenomenon, but later they met together and discussed, and they found both are seeing the same effect, that is nuclear magnetic resonance. Okay, so that was 1946, and they both got Nobel Prize in 1952. Now, in 1966, then there was a major revolution, another major revolution. So this is the first application of Fourier transform spectroscopy to magnetic resonance. Till then, people were sweeping the magnetic field to find the resonance. So RF frequency was fixed. You slowly ramp the magnetic field until you see the resonance. But here comes Richard Ernst. So he started doing pulsed NMR. So you fix the magnetic field, but you send a strong pulse of radio wave. Okay, so that's pulsed NMR, and it's also called Fourier transform spectroscopy. The idea is like this. So if you have a piano, okay, so this is from Ray Freeman's book. It's a very famous book. He calls it as spin choreography. And so what he says is, if you have a piano and you want to find the resonances of each, so basically you want to find the frequency of each key. One way is to press each key at a time and record the sound, and you get the period and you can get the frequency. But that's a very slow process. That was what Bloch and Purcell did. Okay, so slowly change the magnetic field until you hit the resonance. It's a very slow process. The other way is that you take a bar and hit all the keys simultaneously, okay, and you get a horrible sound, and you then do Fourier transform. Okay, then you get all the frequencies in one shot, right? So that's the idea of pulsed NMR. So you don't need to hit individual keys one at a time. You can hit all of them simultaneously and then do Fourier transform. Okay, so now you don't have to do sweeping. So you hit all the frequencies. So it's a complicated beat pattern. Okay, so it's a superposition of all the frequencies, and you Fourier transform, you get all the components in one shot. So earlier it was taking a long time. It was taking several hours to record one spectrum. This takes 1 second. Okay, so that's the power of this Fourier transform NMR. And so again, Ernst also got Nobel Prize in 1991 for the development of Fourier transform NMR. So you will see slowly through the talk why this is important. So Ernst says very interestingly, so he says that the first successful Fourier transform NMR experiments were done in the summer of 1964. The response to our invention was, however, meager. The paper was rejected twice by JCP, Journal of Chemical Physics. the referee kept on saying that it is useless. Okay, and to be finally accepted and published in Review of Scientific Instruments, which is also a very popular journal, but they were more receptive. There were two companies at that time. One was Varian. Varian also resisted to build a spectrometer that incorporated Fourier transform concept. It took many years before the competitive company Bruker demonstrated in 1969. And Varian is closed now. Bruker is there. So that company got shut down a few years ago. So now, so that is the story. So that is a moral number 2, that if your paper gets rejected once or twice or more, so don't worry, something is waiting for you. So he got Nobel Prize in 1991. Okay. No, no, no. Yeah. Yeah. FTIR came even much later than FTNMR. Yes, FTNMR came first. Yeah. Yeah. So CWESR was there. FTIR was. Yeah.
What was the magnetic field in all those experiments?
So in these experiments, I think it was less than a Tesla, so probably close to a Tesla, but they were electromagnets. They were not superconducting magnets. Okay. So I think maybe half a Tesla or something at that time. Yeah.
No, because I'm asking like you were showing 15 or 12 Tesla, right? That
No, that's the status today.
no,
Okay.
I
Yeah.
understand.
Yeah.
That's
Yeah.
But why then they were able to see so low magnetic field?
Because superconducting magnets were not available at that time. Okay. Now we use superconducting magnets. Yeah, so what? No, no. See, electromagnets beyond 1 Tesla, for example, they become so heated up. All right, you have to do water cooling and all those things. It's a elaborate setup. Otherwise, if you don't have elaborate cooling system, electromagnets can't take you more than 1 Tesla or 2 Tesla. Okay, so that is the current electromagnets. Yeah.
How could they then they see the same resonance?
So resonance. So see.
Even splitting, that is like you got in gigahertz because of such large magnetic field.
Correct. Today.
Yeah.
Today.
But
Yeah.
what about then?
That time it was proportionately, so yes, proportionately small. So the Larmor frequency is proportional to the field. Okay, it's linear dependence. Okay, so that may be about 50 megahertz, for example. Okay, 50 megahertz, 40 megahertz, and so on. Yeah. So today we are talking about 500 megahertz, 1 gigahertz, and so on. Okay, so then comes its applications. So one of the very interesting facts people found that the nuclear magnetic resonance signals, they are very sensitive to chemical environment of the nuclear spin. So for example, all these dots here, they are hydrogen atoms of a macromolecule. It's a protein. So they are all hydrogen atoms. Okay, there are so many hydrogen atoms in this. Okay, all the dots. But they are all hydrogen atoms, so they must be having same property, right? However, if you record, you get that spectrum. Okay, so it's a complicated spectrum. So that means every hydrogen atom is contributing to some particular line here, depending on what is the chemical environment. Okay, so that's how the information about the chemical environment is hidden in the spectrum. And slowly it was realized that it not only holds the information about chemical environment, that means which group it is belonging to, whether it is aliphatic, aromatic, all information is there in this position of the peak. Not only that, it can also give information about mutual distance. Okay. It can give information about the distance between the two hydrogen atoms. So that means if you can cleverly collect all these resonance peaks, and you can collect all the distance information, then you can work out the structure, three-dimensional structure, right? So then the next thing is more recently, it is now realized that it can also give information about the dynamics. Okay, whether the protein is unfolding and folding or stretching this way or that way, it can give complete tensor information about the dynamics. So Professor Anil Kumar from IIC Bangalore, your neighbor, so he was the first person to obtain this three-dimensional structure of a protein using something called two-dimensional NMR. Okay, so it was a landmark paper, and so that is one of the papers that Richard Ernst cites in his Nobel lecture. So, by the way, that work he did when he was with Richard Ernst. And then, so as you can see, it is so crowded. It's very hard to get information from this. Then people developed multi-dimensional NMR. So like 2D I mentioned. So you can also obtain 3 dimensions. So that means, so you can have all the nitrogen frequencies here, carbon frequencies here, hydrogen frequencies there, and so on. So they are all correlated now. Okay, or you can have spin distances in one direction, you can have chemical environment in another direction, and so on. So all kinds of, yeah.
What do you mean by multi-dimensional, multiple frequencies?
Yes, multiple properties. Okay, so same spin may be correlated with the neighboring spin. Okay, so that is the spin-spin interaction. In one axis you have spin-spin interaction. In the other axis you have which group information. And you can have nitrogen information in, so because if you take a protein, yeah, so, yes, you have to put different RF fields according to the resonance frequency of different isotopes. Okay, hydrogen will have one resonance frequency, carbon will have another, nitrogen will have another. Simultaneously, you have to apply radio frequencies on different isotopes. Okay. So there are different varieties. So there are hundreds of multi-dimensional NMR experiments depending on the information that you are seeking. So that was developed by many people, most importantly by Kurt Uttrich. He showed that you can take NMR spectroscopy to very large molecules. For example, molecular weight is 500. So this is 10,000. With 2D you can go up to about 10,000. With 3D you can go up to 30,000 molecular weight. Now you can go up to 100,000 or even beyond. Okay, so that's a huge molecule, but still you can resolve all the peaks and get 3-dimensional information, structure, dynamics, everything. And so Kurt Uttrich got Nobel Prize in 2002. Now this is while all these things are going on in spectroscopy, so there was another parallel work was going on. So this is very interesting. So this has another model. So this was Lauterbur. So what he did was, okay, so you are doing routine experiments with homogeneous magnetic field with one sample and so on. He decided to make the field inhomogeneous, and he, instead of putting one sample, he put 2 samples. That's all he did. Very, very simple experiment. Inhomogeneous magnetic field and put 2 samples. So when he did that, to his surprise, so he had 2 water tubes and he got 2 spectrum, so 2 patches. Okay, so in the signal, he got 2 patches. So this is explained like this. There is a field inhomogeneous, field inhomogeneity in this direction. So you get one projection like this. There is a field inhomogeneity in this direction like this. So it is the projection reconstruction method. Okay, so basically you are applying field inhomogeneity in different direction and you get different projections, and then you can reconstruct this. Okay, that's all he did. Pretty much that's all he did. That's the most important work he did. After that, he went on to do something else. And so there is a third moral here. So your experiment may be very simple, but it may be having very high impact. So because that's what led to MRI. Okay, so that is the basis of MRI, that you have a patient here and you have magnetic field gradient here, and you have radio waves. It is basically nuclear magnetic resonance imaging. They dropped N because nuclear word was scaring patients. So they just dropped nuclear. So it is left with MRI now. Basically it is same as nuclear magnetic resonance. And so you apply radio waves and you resonate whatever part you want. So you can resonate brain, you can resonate liver, whatever part you want. Okay, so you can resonate. And then you can do this imaging. So instead of projection reconstruction, Anil Kumar again, he made a revolutionary discovery, a revolutionary methodology development. So he said we can again do Fourier transform. Okay, so it is very fast. You don't have to do multiple projections. Just in one shot, you can do Fourier transform imaging, and that was the first experiment. And I was lucky to be his student. Okay, so so he is retired now. And so that led to very powerful MRI techniques, which are very fast now. So now you can get very elaborate and intricate, non-invasive. NMR is non-invasive compared to CT scan, because CT scan is a ionizing radiation, right? It is a high energy radiation. And radio waves are completely non-invasive. It is not at all harmful. It doesn't ionize. It doesn't lead to any side effects. And probably side effects are caused by the contrast agent that you are taking. Otherwise, radiation itself is not a problem here. Okay, so that is the basis of MRI. And so Latterbohr, so the original two-tube experiment, he got Nobel Prize. So that's in 2003. Okay, so that's a very simple experiment, and that's the moral number 3. So that experiment may be very simple, but impact may be very, very high. Yeah. Yeah, so very high magnetic field are bad, but so now MRI machines are rated and licensed for up to 2 Tesla. Okay, most of them are 1.2 Tesla. Up to 2 Tesla, it is rated as safe. Yeah. Beyond that, it is not rated. It is not advisable for human MRI. In fact, when the patient is moving in and out, that is the dangerous part. Steady magnetic field is not dangerous. The gradients are dangerous. So that's why up to 2 Tesla it is safe. Okay, so that's the story of MRI. Okay, so now, so here is the summary of nuclear magnetic resonance again. So you have a magnet, very strong magnet. So it is generated by superconducting coils. You have hundreds of amperes of current. Okay, normal power here has about 10 to 15 amperes. So there is 100 to 200 amperes of current, very high. But once it's a closed loop. Once you send in and then seal them, it's a very interesting process how they do it. So it's a closed loop. Then it keeps on circulating for several years. So 30 years, 40 years, it's fine. Okay, so it keeps on generating magnetic field. So without loss. And so then you have a RF coil here. So basically it's a Helmholtz coil, and you have sample here that can be any molecule that you are interested in, and you have nucleus here, and nucleus has a spin that interacts with the magnetic field via Zeeman effect, and you have energy gap, and that is resonated by radio waves, and you can create all kinds of superposition states, and they live for a certain time. Now we want to extend that time. Okay, so we want to make sure that this superposition, whatever we have prepared, lives long time. Okay, so that is what we are interested in. And so here is our NMR research center at IISER Pune. You also have a very nice NMR spectrometer here. So now what we want is ultimately, so we want large registers. So for example, fully controllable, I mean that we should be able to control the state of all the qubits here. So here there are 12 qubits, here there are 12 qubits, here there are 38 qubits. So we should be able to control the states of all the 38 qubits, okay, in this. For long time, how long? So that is what we want to see, okay, how long we can extend. So normally we can do for seconds, can we extend the lifetime, okay. So now, so as I said, so there is no single spin here. So there is a averaging of all the magnetic moments. So that comes back to Savan's question. So we have average magnetic moment. So we have magnetization here. That is a Curie's law. It is proportional to field and inversely proportional to temperature. So basically it's a nuclear paramagnetism. And then we can cause dynamics by radio waves. So we can apply various pulses. Say we can apply X pulse, then it applies a torque along X direction. We can apply Y pulse, it applies torque along Y direction. So we have elaborate and very precise control on the nuclear spin dynamics. Now, so let's say we have thermal magnetization, which is parallel to the magnetic field, and now we apply a 90-degree pulse, and it has come to XY plane. Okay. So magnetization is in the XY plane, but now there is a Zeeman precision. So it is precessing in this, but there is a Helmholtz coil. So now you can imagine this as a dynamo, right? In dynamo also there is a magnet inside a Helmholtz coil, and what it produces EMF, right? Exactly same thing happens here. So it is producing EMF. and that is the EMF it produces. And you can see that it is oscillating as it should, because it is precessing with certain frequency, so the EMF also has the same frequency. However, it is also decaying. Okay. Now that decay is the relaxation. Okay. So that's how it is losing the memory of the state. Okay. So whatever state you have prepared, it is gradually losing, and ultimately it goes back to its thermal equilibrium state. So any non-equilibrium state goes back to thermal equilibrium state. And so when you have collected enough sample for enough time, then you do Fourier transform, and then you can get the frequencies. So in this, there is only one frequency. In this, there are multiple frequencies, and you can analyze and so on. So this is basically nuclear magnetic dynamo. The decay is facilitated by noise. Now that's how memory is limited by noise, and noise is ubiquitous. You can't completely suppress all the noise. Okay, noise is there everywhere, and you have to see what best you can do. Okay. Yes. So what are the sources of noise? So random fluctuations caused by thermal motions of molecules. Okay. So molecules are not idle. You take liquid molecules are tumbling, and all kinds of motions are going on, vibration, tumbling, and so on. You take solids, there are vibrations again, thermal motions. And so see, these are all magnetic moments. So they are all having local fields due to the presence of all other spins in the neighborhood, right? And so if there is motion, then the local field oscillates, the fluctuates. So that is the noise. Okay. So in addition to external steady magnetic field, you have fluctuating field due to the presence of the neighboring spins, which are also undergoing motion. Yeah.
Is it possible to reduce that effect by making it more dilute or something like that?
Yes, that is one way, but still this every molecule is tumbling, and you have to you can't make it too dilute, otherwise you will compromise on sensitivity. All right. So and there are many other things. For example, unwanted interactions, spectator spins, intra and intermolecular interactions. There can be intramolecular effects. So by diluting, you can't suppress that. And paramagnetic impurities. Their sample is not 100% pure. Okay, even if you buy from Sigma Aldrich, which some of you know, they quote that it is 99% pure. That means 1% can be anything. Okay, so unpaired electronic spins, there can be paramagnetic impurities. Instabilities in magnetic field, external magnetic field itself, even though it is a superconducting magnet, it is not 100% stable. If a person walks by, it fluctuates. The field also fluctuates. And electric, magnetic, electromagnetic disturbances, and so on. All kinds of, you have HDTV and you have satellite signals, everything. So there are electromagnetic disturbances, everything. So noise is ubiquitous. So now what best you can do? So what is the effect first of all? So we look at two different processes due to noise. One is something called dephasing noise, or the Z noise. So this can be modeled by this. So you have a Hamiltonian, this is the Zeeman term, and so that is basically a Larmor precision term, and you have a noise term. Okay, so that is so this is sigma z here. So it is same direction as the magnetic field. So basically, it is like external magnetic field itself is fluctuating, as if that. Okay, so that's why it is called z noise, and so that's how you can model dephasing noise. The effect is that the diagonal elements of the density matrix, they are populations basically. The populations in the ground state and excited state, they don't change. Okay. They are impervious to this noise, whereas the off-diagonal elements, they decay. So they are the coherence, they are the quantum superpositions. Okay. So these diagonal elements, they are the populations, they hold classical information, either 0 or 1, how much, how many spins in 0, how many spins in 1. So that is the diagonal term, and they are not affected by Z noise, whereas off-diagonal terms, which are the superposition of the two states, so they decay. So quantum memory is decaying. And ultimately, it goes to this state, that is the steady state, so which has only populations and no coherence. Okay. So that is the process, and that can be modeled this way. This was given by Bloch's phenomenological equation. So dm by dt of transverse magnetization, x and y, the x and y are the superpositions, quantum superpositions. They decay according to this, and solution is the exponential decay. And so ultimately, you just don't have x and y magnetization. So that means you are left with only the z magnetization. Okay, whatever x and y you have prepared, that is lost. Okay, so the quantum memory is lost. Okay, So that is the T2 process. Okay. Now, although I am talking about all these things in the context of NMR, this language is common in many other techniques. Even in superconducting qubits, they talk about same T1, T2. Okay. Even in so I think ion trap and everywhere you can talk about T1, T2. Okay. So basically, this tells about how diagonal elements decay and how off-diagonal elements decay. So the idea is common. So this is the energy conserving process, dephasing or incoherence process, and it erases quantum memory. And in NMR, it is of the order of few seconds. So that's where you can see there is a border, there is a barrier. Okay. Now there is another process. So the populations which imbalance that you have created, that also doesn't stay constant. So that is the classical memory. Okay. Suppose by doing RF pulse, you do population inversion. Okay. So you have taken higher population to excited state and lower population to ground state. Right? So that is possible by spin flip. Magnetization is inverted. How long does it stay? It doesn't stay forever. Okay. After some time, you will see that it has gone back to Maxwell-Boltzmann distribution. So excited population has less population, and ground state has more population. Okay. So how that can happen? So that needs energy exchange. Okay. So there is a interaction between spins and lattice, because it has to exchange energy with something. It exchanges energy with lattice. And so that is the spin lattice relaxation, and that is given by this, where mz is the z magnetization and m0 is the thermal equilibrium magnetization, and that is that goes by a time constant T1, and so it is called T1 process. It erases both quantum and classical memory. Okay, and again this is also of the order of seconds. Everything is in room temperature. You can do at a little bit higher temperature or lower temperature. Yeah. We can reduce to low temperature, but if you want to go to 100% ground state, okay, then you need to go take the sample to micro Kelvin temperature. Because NMR energy gaps are of the order of micro electron volt. Okay, so you need to take it to micro Kelvin. Yes. It doesn't change anything. Yeah. 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 Right.
So is the setup here that you apply a magnetic field pulse and then you don't apply magnetic field?
Yes. Yes. This is what it is.
So if you keep a constant magnetic field.
So that is a very interesting thing. So if you keep applying a radio wave, then there is a steady state which is neither thermal equilibrium nor the original initial state. It goes to some steady state in the combined effect of relaxation and the drive. So that's a complicated problem. In single spin, it is solved, analytically solvable. But the moment you go to two spins, it becomes all complicated. Yes. Yeah. So now we can clearly see that there are barriers, and now there is a fourth. Moral of the story. So you see, you hit a barrier, and when I was a PhD student, so I was told by all the textbooks, by everyone in the NMR community, that this is unsurmountable. Okay, so this is the barrier. You can't think about anything beyond that. Okay, so we were told you measure T1, T2, and then NMR stops. Beyond that, there is no NMR, and so you just have to change the sample to get better memory. Okay, so there is nothing you can do about it. So lifetimes of non-equilibrium states are limited by T1 and T2. In spectroscopy, sensing, precision, everything is goes like 1 by T1 or 1 by T2. So all these things are limited by T1 and T2. Okay, so all the applications are limited by these two barriers. But so that the year I finished PhD, so this man comes, Malcolm Levitt. He published a paper. He says beyond the T1 limit, singlet nuclear spin states in low magnetic fields. Okay, so he published this paper in PRL. So he says there is a way out. You can go much beyond that. Okay, so that's rule number 4, moral number 4, that never believe in literature too much. Okay, so when somebody says something is impossible, there may be a way around it. Okay. So possibility of he showed that there is a possibility of long-lived nuclear non-equilibrium states which live much beyond the normal T1, T2. Okay, and in spectroscopy sensing, again, these are very important. So you can do better than this. Okay, so NMR doesn't limit you to T1, T2. You can go much better than it. So that's a revolution, and it has now opened a new branch. Okay, there are textbooks being written. There are huge technology being. There are funds being pumped into this, and so on, because it has now developed altogether different dimension now. So the idea is the following. So you take now 2 spins instead of 1 spin. Okay. Now if you take 2 spins, and if this is the Hamiltonian, then these are the eigenstates. So, so this is like sigma 1 dot sigma 2 or I1 dot I2. Okay. So there are 3 states. These are called triplet states, and there is one state which is the ground state, and this is the singlet state. And if you see the symmetry, this is 0, 1, minus 1, 0, and if you exchange, it will change the sign. So it is antisymmetric with respect to parity. And if you exchange any of these, they are unchanged under exchange. So they are even with respect to parity. Okay, so they are all symmetric. Now it was found by Malcolm Levitt that most of the noise processes, dominant sources of noise processes, they are also symmetry preserving processes. Okay, like dipole-dipole interaction. They don't change symmetry. Okay, so that means if you somehow put the magnetization in this state, okay, if you populate that state, then it is locked, because the noise cannot take from antisymmetric state to symmetric state. So that state is locked now. Okay, so now that was the idea, and then when I will show you some experiments. So this singlet has 0 angular momentum, and so it is non-magnetic. It is unperturbed by collective noise. If anything that has collective noise, which is same on the both spins, okay, and that is symmetry preserving, then it is locked. So it may far outlive T1, T2, sustain for minutes, hours, or even longer. Okay. So whereas T1, T2 seconds, they found that this can be very, very long. It is like 50 times longer than T1. It is reported. Okay, up to 50 times T1, T2. Yeah. Correct. Yeah. So the way phonon couples to the nuclear spins is via dipole-dipole interaction, because you see phonons are basically lattice vibrations, and there is one spin here, one spin here. During lattice vibration, there is a relative moment. Okay, and the way that is sensed by the other spin is because of the local field fluctuations, right? By the two. Suppose there is a oscillation here, the local field changes, and that is the dipole-dipole interaction. And dipole-dipole interaction is a symmetry preserving process. It cannot change the symmetry. It cannot take antisymmetric state to symmetric states. It can convert from one triplet state to another triplet state very efficiently, because they are all symmetric. But it cannot take singlet state to triplet state. Okay. So, yeah. Yeah. Via dipole-dipole interaction. Because spin is a magnetic moment. It can talk to either magnetic field or another magnetic moment. Okay, so not directly to phonon. So via these spins. So it may far outlive T1, T2, sustain for minutes, hours, or longer. So now spectroscopy of long-lived states, it's a new branch of NMR since 2004. So what Levitt did was very ingenious experiment. This is a picture from his PRL paper. So he prepared a singlet state, and he showed how to prepare singlet state, and he just lifted the sample out of the magnet. So he built a pulley to the ceiling. It's a very interesting experiment. He put a pulley in his NMR room and lifted the sample out of the magnet, and then he could wait for some few minutes. He kept the sample in his pocket and then loaded it back to the magnetic field. See, singlet is non-magnetic. It doesn't need magnetic field. In fact, it lives happily without magnetic field. Okay, so you can go for lunch and come back and put the sample, and it still keeps that memory. Okay, and yeah. Yeah.
So in the sample there are many spins.
Yeah.
Right? So how do you prepare pairs of singlets?
Yeah. So initially, in initial experiment, they took a molecule which has only 2 spins. Okay, so others are all non-magnetic For example, you take spin 0 atoms. Carbons are all spin 0. Carbon 12 is spin 0. And there are, say, there are no other carbons and no other hydrogens. Okay. And then it is a non-magnetic. Okay. So they took such molecules, or you can take deuterated samples. Deuterium is weakly magnetic. Nuclear magnetism is very weak. Or you can take oxygen. Oxygen O16 is again spin 0. Yeah.
In the same molecule.
Same molecule. Yes, yes, same molecule. Okay. Yeah, I'll show you some molecules. No, no. This is ensemble. It's a 0.5 ml of sample. Okay. 0.5, and you can keep the quantum superposition in singlet state for an hour. Okay. So in thermal, in ambient temperature, ambient pressure. Yeah.
No, I'm still not understanding how lattice vibration can be decoupled, because lattice vibration Hamiltonian giving me
First of all,
A plus A dagger,
yeah.
so the displacement with the spin
Yeah.
on I1. So
Yeah.
it's not like I1 dot I2 directly coupled to lattice vibration.
Yeah. So you see, yes, you are right. There is a spin-spin interaction in this molecule. Okay. That's the Hamiltonian coming from the spin-spin interaction. Okay. So that is already there. This Hamiltonian is already there. And there is nothing else. When you lift it out of the magnetic field, there is nothing else. Okay. So that's the Hamiltonian.
So the lattice vibrations have some characteristic wavelength, right?
Yes.
So how is that wavelength compared to the distance between these two molecules?
See, I think lattice vibrations, it has wide range of noise, right? It is not just a delta function. It is a band actually. Whatever it may be, so it cannot change the symmetry because of the dipole-dipole interaction. That is spin symmetry preserving.
Yeah, so that I understand, but even so you're saying that this is sort of block diagonal in singlet and triplet.
Correct.
It can also have something that acts on the
Yeah, there are other noise processes like paramagnetic impurity. 100%. There is sample is not 100% pure. There may be some copper sulfate, some paramagnetic impurity in the sample. Those things are fine. I mean, they can cause trouble. Okay, so that's why slowly there are other mechanisms. Slowly it will decay, but still you have removed one of the dominant process of noise. Okay, so that that extends the lifetime. So now there, okay, recently, okay, then after that he came up with another sequence. Now you don't have to lift the magnet sample out of the magnet. You apply something called spin lock. So this is by RF radio frequency only that enforces the symmetry without lifting the sample out of the magnet. Okay, so this is the standard method now. We don't lift the sample out of the magnet. We just enforce the symmetry using spin lock. So now this is the example. I was saying that I'll show some examples. So this is one of our experiments. So you take 2 hydrogens of this molecule. So you can prepare it in a singlet state. And so this is 16, it lives for 16 seconds. And here we have not taken care to purify the sample and all those things. Just without much care, it lives about 5 times longer than T1. Okay, so ordinary sample with ordinary preparation, and so it lives for 16 seconds. And what we noticed was, interestingly, so this was one of the first observation, that if you see what is the fidelity of the singlet state, we did quantum state tomography, and we found that it starts with about 0.8 and it gradually increases. It becomes very high, very close to 1, and then slowly it starts decreasing. Okay. Initially, we couldn't understand what is going on because fidelity in most of the experiments goes down exponentially. But here is the experiment where fidelity increases initially and then gradually decreases. Then we explained it this way that so during the preparation, we not only prepare singlet state, we also prepare a little bit of triplet states. Okay, that's how the sequence works. So there are other triplet states, T0 state, T plus state, T minus state, but they all have normal lifetime. They all decay. They are all sensitive to normal noise, and they all go to under the presence of this Waltz spin lock. They all go to identity. Okay, because I showed the dephasing noise. It takes only diagonal elements, and it keeps only diagonal elements and decays the off diagonal elements. So that becomes identity, and what is left is only the long-lived part, and that is the singlet. And that's how the singlet purifies itself. The fidelity of the singlet improves, and after few seconds it is maximum and then gradually decreases. Okay. Yeah. Yeah. So all the impurity states, they are short-lived.
So you mean to say
Yeah.
that the total thing comes up, but
Yeah.
because the impurity goes down,
Yeah.
the purity.
Exactly.
So
Yeah.
is that like some sort of effective purity that is increased?
Yeah.
And when you say fidelity, it is with the maximally entangled state.
Yeah. So singlet is maximally entangled state.
So now,
Yeah.
is it possible that your
No.
fidelity?
If you consider identity also, it is not maximally entangled.
No.
If you consider only
fine.
singlet part, it is maximally entangled.
No, because I'm thinking that is it just because you see entanglement itself will not change, right? Like your fidelity is changing. So is it getting
Yeah,
some sort of a
entanglement
distribution?
can change here because it's a non-unitary operation. Entanglement also can.
So then
yeah.
there is a system environment
Yeah,
scenario.
yeah,
The
yeah.
overall remains
Yeah.
okay, but you're distributing.
Correct.
A bit similar to this
Yeah.
problem we have been discussing. So
Yeah, I see.
that is what you're also seeing. So overall, because how can it increase?
That's the thing.
yeah.
No, initially we were surprised,
Yeah.
but now there is an explanation because all the impurity states are short-lived. So they have to decay by T1, T2. So what lives is only singlet, which is decaying much slower.
So as a result of which the effective fidelity seems to increase.
Yes. Okay, so then there were many techniques developed for efficient preparation of singlet state. One of the things is sensitivity, because you need singlet state which are very sensitive. One problem with the contrast agents given in MRI is that they are based on some chemicals, and generally they use carbon spins because carbon has some other advantages. Carbon 13 is the isotope which is spin half, carbon 12 is spin 0, non-magnetic. But carbon natural abundance, carbon's natural abundance is 1%, carbon 13. Okay, rest is 99% carbon 12 which is spin 0. Carbon 13's natural abundance is 1%. But carbon pair 1% into 1%. So that is 1 in 10,000. Okay, so this is the problem in MRI contrast agents. So what we developed is we developed a method where a large number of protons can donate the magnetization directly to the singlet pair of this carbon-carbon pair. Okay, so then that increases the sensitivity by 23 times, and so that is so we use something called bang quantum control and so on, so that we can see very easily now singlet states in carbon-carbon pair in the ordinary conditions. You don't need any high field magnetic field and so on, high magnetic fields and so on. You don't need cryoprobes and sophisticated instruments. Normal NMR magnet can do, and so we can improve the sensitivity by this method. So this is another thing. I'll just give some slides on some recent work. So this is the adiabatic method. So people also shown that using adiabatic method, that means you start with the ground state of some other Hamiltonian, and slowly you take the Hamiltonian to the singlet I1.I2 Hamiltonian. So if the process is slow enough, it is adiabatic, system always remains in the ground state until you reach the final Hamiltonian where the ground state is the singlet state. Okay, that's how you can prepare. But then problem is slowly at some stage you get those energy levels coming closer, and that's where the adiabaticity breaks down. And recently there is a new method that is called counter-diabatic method. Means you introduce an additional term. So this is called counter-diabatic term, and in this case, in the case of NMR, so this is of this term, and then you can drive the you can change the Hamiltonian very fast. Okay, so for example, this is the adiabatic method. For slow process, it works fairly well. So the fidelity is 0.5, it's good. But when you try to make it fast, okay, then it fails. Whereas this CD method, counter-diabatic method, it works well even for fast drives. Okay, so now people are thrilled with machine learning. Everyone wants to do something with machine learning. And here is the method. Machines can also do, machine learning can also give the sequence for singlet preparation. So we took a neural network. So we gave the initial Hamiltonian, we gave the final Hamiltonian. So we want singlet state, and we asked the machine to find the sequence, to find the Hamiltonian, which can give us singlet state. Okay, so it is the neural network. And so there is a very interesting advantage of this neural network. So in most of the control methods, we discretize the pulse so that we can calculate the propagator. So we calculate individual propagators and then we multiply and we get the total propagator. Here we don't have to do that. These nodes of the machines, they hold complete information about the shape of the drive. So this is the drive. Finally, it obtained this drive. And the shape, complete information about the shape of the drive is generated and it is encoded in the nodes of the neural network. Okay. So, and then you can discretize later to any precision you want. So that's the advantage. Okay, so the last interesting thing I wanted to show you about my work is that, so recently we wanted to see whether singlet is long-lived enough to survive a phase transition. Okay. So we took a liquid crystal, so it is in partially oriented phase, and if you heat up, it will go to isotropic phase. Okay. It's a pneumatic liquid crystal. If you warm it up, it goes to isotropic phase. So we prepared singlet in this state and then went through the phase transition by warming up and then recorded this. It is the, to our knowledge, this is the first demonstration of long-lived singlet state in liquid crystal NMR as well as survival through the phase transition. And so here is the result. So it took about 17.5 seconds to go to the isotropic phase. Still we had the signal. So this is the original signal, and this is the signal which has survived the phase transition. Okay, after 17.5, and if you wait longer, it gradually decays, and from this we can estimate what is the lifetime of the singlet state in this case. Okay, so that helps us to understand the phase transition. So we are working on this. So now we have a quantum probe which has lived through the phase transition. So we can use that now to understand the phase transition itself. The dynamics of the phase transition and so on. The other thing, interestingly, that can be done, this is just a proposal in this paper. We have not yet demonstrated it. So other thing is, suppose we have a system which allows us to access singlet state in the liquid crystal phase. And in the isotropic phase, it becomes perfectly equivalent. That means the singlet is now locked. So in the isotropic phase, it is locked. So then moment you have it in isotropic phase, you can take it around and then again cool it, you get singlet state. So this, we are still working on this. So this is, we call this as padlock, where we can change the phase transition. We can induce the phase transition and lock the singlet state. Okay, so one last thing. So this is about multiple pairs of singlet. So it is not that only 2 spins can be put in singlet states. We can prepare pairs of singlets. So in fact, this is aspirin. So when we did this experiment, some doctors also called us. So what are you doing with aspirin? So this is aspirin compounds. It has 4 protons, and we can prepare singlet here, and so we can couple them. In fact, it becomes 4 spin entangled states, 4 qubits. Okay, so that's how we plan to increase the register size and memory. So we want to go to, that is the sweet spot. We want to go to large number of qubits and long-lived. Okay, so I want to maybe in next couple of minutes, I want to show you some of the future directions. So there is one thing that is called long-lived coherence. So we have a long-lived state here, and we have a triplet state here. If we prepare superposition between these 2 states, that is also very long-lived. It's a now, so till now I was talking about singlet population, but now we can create superposition. It's a coherent superposition between singlet S0 and T0. It turns out that that is also long-lived. Okay, so that is called long-lived coherence. And so here is the demonstration. So if you take this compound and prepare long-lived coherence, and so before long-lived coherence, this is the normal coherence. So that dies in 1 second. Whereas if you prepare this LLC, long-lived coherence, so that lives for about 100 seconds. Okay. So now you can see that the precision has increased by T2. So here it is a few hertz line width, and so the precision is 0.8 hertz. Whereas here the line width is millihertz, and so again you can measure the J coupling up to 4th decimal. Okay, so that is the Fourier transform of this peak. Okay. So you can get very high precision beyond T1, T2. So all the textbooks, even today, all the textbooks, say that T1, T2 is the barrier, and it is not the barrier. So singlet state gives much more liberty beyond the T1, T2. And so this is a future direction. So what people do in MRI is that you give patient a contrast agent, and that gives you contrast, that is selectivity and sensitivity. Okay, so patient is given some contrast agent before MRI, and that gives contrast as well as sensitivity. But that is not enough. For example, lung MRI, where there is very less tissue density and so on, or brain MRI in some place, there is very less tissue density. So there you have to do hyperpolarization. There are ways, different ways of doing hyperpolarization. That means you are increasing the magnetization by doing hyperpolarization. That gives better sensitivity, but not improvement in contrast. Now you can do hyperpolarization and long-lived state, so which will improve both contrast as well as sensitivity. So this lot of funding is going on in Europe as well as in US in developing this. If that works out, MRI price will come down because you don't need such a strong magnetic field. Okay, so you don't need 1 Tesla. MRI can be done in much lower fields because you already have better selectivity and sensitivity. Yeah, so there are, in conclusion, there are diverse applications of NMR already. So starting from MRI and structural biology, medicine, and so on. And of course, quantum, it's considered as a quantum workshop. We can do all sorts of quantum simulations. And so on top of this, long-lived states, they are opening exciting applications which have importance in physics, chemistry, biology, and medicine. I will leave you with this, and I'm happy to take questions.
So thank you very much, Professor Mahesh, for the excellent talk. There are many questions. Shawan.
Yeah, so initially you said you have a qubit with 2 levels and that you can apply magnetic fields and work on the Bloch sphere and so on. But now if I produce a singlet state, I mean, in some sense the net magnetization is always 0. So what sort of manipulations am I thinking of now? What is my qubit?
Yeah, so magnetization is 0, but
Yeah.
you can label that as 0 qubit, 0 state of the qubit. Now T0 you can label as 1.
Okay, so you're thinking of singlet and triplet as the 2
Yeah,
levels.
that's the qubit. Yeah.
But how is it the triplet is also long-lived? I thought you said that the symmetric sector is...
Yeah, so there is a detailed theory on that. So what happens is, so part of the amplitude is in the singlet state, partly in the T0 state. So you have, so part of the state which is robust against the noise, part of the, so that is contributing to this. Okay, so beyond that it is hard to give a naive answer, but there is a detailed, very sophisticated theory to explain that. Yeah. Yeah. Basically, it is putting 1 foot in the long-lived state and 1 foot in the normal state. Yeah.
Yeah. So you talked about beating the T1, T2.
Yeah.
Would it, maybe I'm missing something, but wouldn't it be more accurate to say that any system like this is actually partitioned into 2 systems, 2 subsystems? One is a singlet part and one is a triplet part, and the singlet part will have its own T1, T2, which is what you are measuring, as opposed to, describing the system for the entire ensemble, which has the singlets and the triplets.
Yeah.
Because, I mean, if you are going beyond the T1, T2 formalism, then actually what are you actually doing? You're basically saying that there is no channel for decay of the singlet.
Yeah.
I would just say that that's another T1. I mean, the singlet has a
No,
different...
You are completely right. So this is another form of T1, T2, which is not same as the single spin T1, T2. Only thing is, before 2004, NMR community did not know that it can be prepared conveniently and it can be detected conveniently, and it has such diverse existence in wide variety of molecules, or how long you get the advantage, whether it is twice the T1 or 100 times. So now it looks like it is up to 50 times it can exist. So yeah, fundamentally you are right. So instead of relying on single spin T1, T2, we are going for another T1, T2, which is now for pairs. Right? Only thing is we didn't know that such states are possible.
Yeah, the robustness of these states has surprised the community, but
Yeah, one is robustness, another is convenience with which you can prepare and detect.
yeah, sure. Okay. So one more question, if I am allowed. So the thing is that you say that you are going to, I mean, the NMR systems can be used for quantum computing, etc. Right? To do certain classes of. So the thing is that now you have some spin population in ground state, some spin population in excited state. You prepare and you look at how the you put a sequence of pi/2 pi pulses in very strategic locations, etc. But then just to get a feel for what is the readout like of these things. I mean, how does the computational part end? I understand the preparation thing, but then I mean, how do you read back?
Yeah, so as I said, final signal is like nuclear magnetic dynamo. So we have a Helmholtz coil, and then the final magnetization precesses in that, and then that produces a EMF, and that EMF is detected as the NMR signal, and that holds the complete information about the final state. And on top of that, if you want, we can do quantum state tomography. That means basically you are applying different rotations at the end of the experiment, and you can actually check what is the X magnetization, what is the value of Y magnetization, Z magnetization, and so you can reconstruct the complete density matrix.
Okay.
So depending on what is the need, we can either stop at the final magnetization and then check the signal. If that gives fine answer state, that's fine. Most of the algorithms, quantum algorithms, are designed such that you don't need quantum state tomography. For Shor's algorithm, you don't need quantum state tomography. All you need is just the final signal, because the algorithm is designed such that the final population has the answer. Yeah. And this final population can be easily detected by the final NMR signal.
Okay, thanks.
So just to carry on with the quantum computing thing, can I ask the controversial question that you will always get asked, that NMR is an ensemble system, so how does it scale?
Yeah, so it was realized long back in, I think, 2000 itself, that scalability is an issue. In fact, in one of the slides, I showed NMR scalability with red circle. So in that table, so there is a scalability issue. However, so NMR, the idea is like it's a workshop, quantum workshop. We say you can test various things, and so you can apply to various other methods, because the quantum dynamics is same. Today you may develop a method in NMR, and that is applicable to somewhere else. For example, all these Hahn echo, spin echo, and there are dynamical decoupling. They were all originally developed in NMR. And now they are applied in superconducting qubits. The original development was in NMR. So NMR is actually birthplace for many quantum dynamics techniques. All these quantum control methods, GRAPE, the first experiment was in NMR, right? So then it was exported to all other techniques. So we say it's a workshop where you build things, build methods, and then give it to others. Okay.
That's a fair answer.
So how these singlet and triplets are prepared?
Singlet, yeah. So basically, I showed many methods, including machine learning and all those things. The simplest method is that you have thermal magnetization, which is for two spins, sigma Z1 plus sigma Z2. Okay, and for singlet state, the density matrix is ground state of minus I1 dot I2 Hamiltonian, right? Okay. So now there are just 3 RF pulses required. So that is, maybe I should go back. So that prepares singlet state. Yeah, these 3 RF pulses. Okay. So 190 degree about x-axis, 180 degree about x-axis, 90 degree about y-axis. That's enough.
And they both are acting on the both spins.
Yes, both the spins. Yes, both the spins. Yeah.
and that would create an.
That prepares singlet state, and then you can store it for whatever time you want. So that
Now,
is.
is it possible to continue increase the number of spins, because then you can create something even like
Yeah.
squeeze
So when
state.
you have more spins, then you have to do this way. So you have to apply C naught in between and so on. Then you can do for more spins.
More
Okay.
spin
Yeah,
also,
yeah.
like this
Yeah.
way one can extend.
Is this producing a singlet of 4 spins?
Yes. Tensor product of two singlet states. Singlet, tensor, singlet. Yeah.
So I have an extension to Dibendu's question. See, you explained earlier why the singlet state has immunity when it is put in the sample, because you are going to
Non-magnetic state.
yeah, because
so this
yeah.
is a very clever question. So how is it interacted by
Yeah.
RF field? So actually, here is the answer. Singlet is, you are right. Once you prepare singlet state, it is impervious to even RF field, okay, because it is non-magnetic. However, now you see there is this tau 3 delay. This is the storage of singlet. That's fine. Okay, that's just a storage. You can even take it out of the magnet. But now there is a tau 3 delay. So during that time, we don't apply RF field. It's just a delay. During that evolution under the internal magnetic field, internal Hamiltonian takes place. Now, internal Hamiltonian tries to distinguish between the two spins because it has different Larmor frequencies. The two spins that you take have different Larmor frequencies. Okay, so now the indistinguishability of the spins is gone. Okay, so now the Hamiltonian, the reason why there is indistinguishability is because the two spins have different densities of electron clouds. We take the molecules such that they have different densities of electron clouds, and electrons are diamagnetic, they shield the external magnetic field, and so there is different Larmor frequency. This is called chemical shift. And so during this time there is chemical shift evolution, and that can distinguish the two spins. Moment you can distinguish the two spins, their robustness gone. Okay, so they become normal states. So that's why we apply spin lock here to enforce indistinguishability. So we call symmetry switching. So we switch the indistinguishability in this during this time.
Singlet and
Yeah.
tester singlet, it almost feels.
Sorry?
Then you have created
Yes.
singlet, weighted enough to again becomes individual.
Yes,
component.
yes, yes.
So
Yeah. Yeah, so it is like this. If your Hamiltonian is I1 dot I2, singlet is an eigenstate. It can't go anywhere. If it is not I1 dot I2, so in this tau 3, it is not just I1 dot I2, plus it has omega 1 of IZ1 plus omega 2 of IZ2. So the omega 1 and omega 2 are different. Okay, so now it is no longer an eigenstate.
And that is what my question was,
Yeah.
it is earlier also called the Coulomb part, that as soon as you add those two, then how you
Yeah,
select
so
on conjunction
you are right. So there is a process called chemical shift anisotropy, which is exactly what you are saying. Okay, so there is lattice vibration. On top of that, there is a chemical shift anisotropy, which may be different in different spins. The two spins may have different chemical shift anisotropy. That will cause relaxation via phonons, right? But dipole-dipole interaction doesn't distinguish, because Hamiltonian, if you dipole-dipole, because if you exchange two spins, Hamiltonian doesn't change. Yeah.
So what do you do over tau 4 in order to keep it?
Yeah, maybe
Yeah, yeah.
shall we continue the discussion over tea, because and you are here anyway. He is here tomorrow also, and yeah. So thank you so much for this excellent presentation, and also as a token of our appreciation, kindly receive this book on Raman.
Oh, great. Thank you very much. Okay, thank you very much. Yeah, this is great.
So please join us for.
Sure. I
I'm afraid it was too long.